Quick truth about data structure interviews at the senior level, they almost never want you to write one.
Wait, they don't?
No. They give you a scenario and ask which structure you'd reach for and why. Pick wrong, and the whole system design falls apart 3 questions later.
Okay, so teach me to pick right. Last episode was my half. The fundamentals, paradigms, solid, clean code.
And this week's mine. Data structures, the conceptual way. No leak code, no writing code on a whiteboard.
Hang on, data structures are basically my side, the CS fundamentals.
Conceptually, sure, but I'm the one who's watched them blow up in production. So today, you're the student.
Great.
Start with the 2. Everyone thinks they know. Arrays and linked lists. An array is one contiguous block of memory. That's the key. To get element number k, the computer just does base address plus k times the element size. 1 multiply, 1 add. Constant time, no matter how big the array is.
And insertion?
That's the catch. Insert or delete in the middle, and you have to shift everything after it over by 1. That's linear time. A linked list flips that. Each element is a separate node, holding its value and a pointer to the next one. So inserting, if you're already holding the node, is constant time. Just repoint 2 arrows.
But finding the node in the first place is linear, because you walk the chain from the front. There's no jumping straight to index k.
Exactly. Now here's the part that trips people up. On paper, linked lists look better for lots of inserts. In practice, arrays usually win anyway.
Why?
Cache locality. Memory comes into the CPU in chunks. Cache lines, about 64 bytes. An array's elements sit right next to each other, so one fetch pulls in the next several for free. A linked list's nodes are scattered all over the heap, so every hop is a potential cache miss, and the CPU stalls waiting on memory.
The 2 structures with the same, big O, can have wildly different real-world speed.
That's the senior insight. Big O ignores the constant factors, and cache misses are a huge constant factor.
One more thing people miss. The array you use day to day is a dynamic array. It doubles its capacity when it fills up and copies everything over. That copy is linear, but it happens rarely enough that appends a constant time, amortized.
Good ad. Okay, first interview question. I'm asking, you're answering. You've got a collection where you're constantly adding and removing items from both ends, front and back. Array or linked list?
Both ends. So it's a DQ, a double-ended queue. I'd back it with a doubly linked list, so both ends are constant time. Or, if the maximum size is bounded, a ring buffer, a fixed array with a head and tail index that wrap around. That keeps the cache benefits and gives constant time at both ends.
That's the answer. The ring buffer is the one that gets you the nod. Those 2, DQ, ring buffer, lead straight into stacks and queues. A stack is last in, first out. You only touch one end, push on top, pop off the top.
And it's everywhere. You don't think about it. The call stack, every function call pushes a frame, undo and redo, expression evaluation, and depth first search and backtracking, which we'll hit in the graph section.
A queue is the opposite. First in, first out. NQ at the back, DQ from the front. Task scheduling, message buffers, and breadth first search.
Quick precision point. A naive queue on a plain array is a trap. If DQ shifts every element forward, that's linear per DQ. You implement it as a circular buffer, so both operations stay constant time.
Right. And 2 variants worth naming. A priority queue, where you always pull the highest priority item next, that's backed by a heap, we'll get there. And a DQ, which we just covered. Now the one you'll use more than anything else in your life, the hash map. You hand it a key. A hash function turns that key into a number. You divide by the number of buckets and take the remainder, and that tells you which slot to store the value in. Because you jump straight to the slot, lookup, insert and delete are all constant time on average.
On average is doing a lot of work in that sentence. What happens when 2 keys hash to the same slot?
A collision, and how you handle it is the data structure. 2 main strategies. Chaining, each bucket holds a little list, and colliding keys just get appended. Open addressing, if the slot's taken, you probe for the next free one.
And the thing that keeps it constant time is the load factor, the ratio of entries to buckets. Once it crosses a threshold, around 75%, the map resizes. It allocates a bigger bucket array and rehashes everything.
Which is linear for that one resize, but amortized constant time over all the inserts. Same doubling trick as the dynamic array.
Here's the part interviewers actually probe, the worst case. If every key collides into one bucket, your constant time map degrades to linear because you're back to scanning a list. Modern libraries defend against this. Java converts an oversized bucket from a linked list into a balanced tree, so the worst case is logarithmic instead of linear.
And in the real world, a hash map is the backbone of caches, database indexes on exact match lookups, deduplication. A hash set is just a hash map with no values, and Redis is essentially a giant distributed hash map. Your turn to ask me one.
Alright. Your service is running fine, then in production your hash map lookups quietly go from constant time to crawling, linear. Nothing else changed. What are the suspects?
A few things. 1. A bad or predictable hash function, so keys pile into a few buckets. 2. An attacker deliberately sending keys that collide, that's a hash, flooding denial of service. 3. The map never resized, so the load factor is sky high and every bucket is a long chain. The fix is a stronger randomized hash and making sure resizing actually kicks in.
That's the full answer. Most people stop at bad hash function and miss the load factor and the attack angles.
Once you need ordering, not just, is this key present, but, give me everything between X and Y, you move to trees. Start with a binary search tree. Every node, everything in the left subtree is smaller, everything on the right is larger. So searching is like binary search. You have the problem each step. Logarithmic to find, insert or delete.
If it's balanced, and that's the catch you glossed over. Insert already sorted data into a plain search tree, and every new value goes to the right, it degenerates into a linked list. Now it's linear.
Which is exactly why balanced trees exist. They automatically rebalance after every insert and delete, using rotations, local rearrangements that fix the height without breaking the ordering. Two famous ones. AVL trees, kept very strictly balanced, great for read, heavy workloads, and red-black trees, which allow a bit more imbalance but do fewer rotations on writes.
And red-black trees are the ones you've actually used without knowing it. They're under Java's tree map, C++'s standard map and set, and a version shows up in the Linux kernel scheduler.
Next, the heap. It's a complete binary tree with one rule. Every parent is smaller than his children for a min heap or larger for a max heap. So the smallest or largest is always sitting right at the root.
So peaking at the top is constant time, and insert or extract is logarithmic while it resettles. And neat detail, a heap is usually stored as a flat array, no pointers. The children of index I live at 2i plus 1 and 2i plus 2.
And that's what powers a priority queue. Task schedulers, Dijkstra's algorithm, give me the top 10 queries. Last tree, the trie, or prefix tree. Each path down from the root spells out a string, one character per edge, so lookup costs the length of the key, completely independent of how many entries you've stored.
That's the magic. 1,000,000 words in the trie, a looking one up still only costs the length of that one word. Autocomplete, spell checkers, and IP routing tables all run on tries.
Interview question. I'll ask. You're building autocomplete for a search box, millions of possible terms, and it has to feel instant as the user types each letter. What structure, and why?
A trie. As the user types, each keystroke walks one more edge down the tree, and everything below that node is a valid completion. The cost is the length of what they've typed, not the size of the dictionary, so it stays instant whether you have 1,000 terms or 10 million.
Nailed it. Last big family, and the one senior interviews love, graphs, nodes, and edges connecting them. First decision, how do you store it? An adjacency matrix, a V by V grid, where each cell says whether there's an edge. Checking is A connected to B is constant time, but it costs B squared space, whether the graph is full or nearly empty.
So the matrix is only worth it for dense graphs. Most real graphs are sparse. Think a social network, where you follow a few hundred people, not millions. For those you use an adjacency list, each node keeps a list of just its actual neighbors, far smaller.
Then, traversals, how you walk the graph, two workhorses. Breadth first search explores in rings, all the neighbors first, then their neighbors. It uses a queue, and because it expands evenly, in an unweighted graph it gives you the shortest path, fewest hops.
Which is exactly degrees of separation on a social graph, or the fewest clicks between two web pages.
Depth-first search does the opposite. It dives as deep as it can down one path before backing up. It uses a stack, or just recursion. It's what you use for cycle detection and topological sort, ordering things by dependency.
That last one is quietly everywhere. A build system deciding compile order, a package manager resolving dependencies, a spreadsheet recalculating cells, all topological sorts over a dependency graph.
Now add weights to the edges, distances, costs, and you want the cheapest path, not the fewest hops. That's shortest path algorithms. Dijkstra's algorithm is greedy. Always expand the closest unvisited node next, using a min heap to grab it fast. One hard rule: it only works with non-negative edge weights.
And if you have negative weights, you fall back to Bellman-Ford. Slower, but it handles negatives, and it can even detect a negative cycle, a loop that makes the path infinitely cheaper.
And the upgrade to Dijkstra is a star. Same idea, but you add a heuristic, an educated guess of how far each node is from the goal, so the search aims toward the destination instead of spreading out blindly. That's what actual map routing uses.
With one condition that matters: the heuristic has to be admissible. It can never overestimate the true remaining distance. Straight line distance works because the real road can only be longer. Keep it admissible, and A* still finds the true shortest path, just faster than Dijkstra.
Interview question, and this one's a favorite. You need the shortest driving route across a road network with millions of intersections, Dijkstra, or a star, and why?
A star. Plain Dijkstra explores outward in every direction, so on a huge map it wastes time expanding nodes pointing away from the destination. A star uses the straight line distance to the goal as an admissible heuristic, so it stays aimed at the target. Same guaranteed optimal route, a fraction of the work.
That's the one that ends the interview on a high note. We've been throwing Big O around this whole time, let's make it concrete.
It's just a ranking of how cost grows as the input grows. Constant, a hash lookup; logarithmic, a balanced tree search; linear, one pass over a list; linear arithmetic, n log n, a good sort; quadratic, nested loops; and then exponential and factorial, which are the "you've done something" brute force red flags.
And the half everyone forgets: space. Recursion isn't free. Every recursive call sits on the call stack until it returns, so a recursion D levels deep quietly costs D units of memory. That's how a clean recursive solution blows the stack on a big input.
And the senior framing: none of this lives in isolation. The real question is always inside a system. Here's the last one for you. An API endpoint does a linear scan over a table that grows by a few thousand rows every single day. At what point does that become a problem, and what do you do about it?
It's fine at 1,000 rows, and quietly fatal at 10 million. The latency climbs linearly with the table, so one day, a request that took 5 milliseconds takes 5 seconds. The fixes: in order, add an index so it's a tree lookup instead of a full scan, cache the hot results, and paginate so you never return the whole set at once.
That, right there, is the whole reason they ask about data structures. Not to see if you memorized a definition, to see if you can predict where a system breaks.
So, that's the toolbox: arrays and lists, stacks and queues, hash maps, trees, graphs.
And the through line: pick your structure by the access pattern. How you'll read and write the data decides everything.
Next episode, we cross into my actual home turf, the operating system, threads, locks, and all the ways concurrency ruins your week.
Can't wait. See you then.